Okay, so listing the surfaces we have so far. Planes, spheres, ellipsoids, cylinders, uh, paraboloids. Okay, is there any that I'm forgetting here? I think that covers everything we've done so far. Okay, and so with paraboloids, we said that the reference paraboloid, we worked out this one, and we worked it out, and then we saw that there were all these transformations of that, right? There were three transformations. We could translate it, move it, change the axis of orientation by changing the variable that's the linear variable, right? And then we'd have circular versus elliptical by dividing by the radius squared. And we worked all that out in class, last class. Okay, so there's a new surface, which instead of z equals x squared plus y squared, our reference is going to be z squared equals x squared plus y squared. And so this kind of looks like a paraboloid, but this is z squared. It kind of looks like a sphere, right? But if I was to do the math on this, x squared plus y squared minus z squared equals 0. So this is definitely not a sphere for two reasons. We got the minus z squared, it would have to be plus. And then for a sphere, this would be like our radius sphered, or squared. So this is 0, so this is not a sphere, right? So not a sphere, kind of looks close, but not a sphere. All right, so what is this? So when we don't know what something is, we use the approach of the traces. And so we'll just quickly do that here. And the traces I want to use are the z traces. So say 1, 3, and then, and specifically when you're fixing z values, the traces you get are called level curves. Because a constant z value means a constant horizontal value, right? So that those curves will stay on the same level, like the level of a building or something like that. So level curves will be like horizontal curves, right, of the surface. Okay, so what trace do we get for z equals 1? X squared plus y squared equals 1, right? And then x squared plus y squared equals, if z equals 3, we'll get 9, right? X squared plus y squared equals 9. Okay, what about, so notice something else that happens here. Before, with the paraboloid, when we tried negative numbers, we got something non-defined, right? You can't add the sum of squares and get a negative. Okay, but here it works, right? Negative 2 gives me what? X squared plus y squared equals 4. So that's valid, right? So I'm getting circles just the same way we got before with the paraboloid. We got circles. But now what's different? What's different is the radius of these circles was the square root of z. What's the radius of these circles?
It's the square root. Absolute value of z.
Yeah, so it's like, yeah, exactly. It's just z. Or if the z is negative, then absolute value of z, right? So here my radius was square root of z. Here my radius is actually z, which means that as we increase in z, the radius increases exactly just like it, right? So if z is 1, radius 1. Z is 2, radius 2. Z is 3, radius 3. So that makes a different kind of shape than our paraboloid. How is it different?
It's a cone.
Yeah, so the edge forms you have a linear relationship of z and r forming the cone. All right, and then also it lives in the negative territory, right? So for z values that are negative, you get growing circles that are symmetric to positive z values. So what do we get? Someone said it. What do we get for this surface now?
2 cones.
Yes,
right?
exactly. Instead of, so the paraboloid is based on parabolas, right? That radius is like square root of z, but now the radius is z, so it's linear. So we get what's called a double cone. She said 2 cones. And so these double cones, you have the same 3 transformations that we had for paraboloids. We can move it by taking, say, z minus 1, x plus 2 squared, etc. We move the vertex. We can change the axes that it opens on. So this isolated variable over here, by making that y squared or x squared, we can change the direction that it opens. And then we can make it elliptical, again, by dividing out by radius squared. Okay, so let's just take a look at a pretty version of this reference paraboloid. So can you guys see that? So here's the pretty version. So those are the level curves, right? And those level curves are kind of giving us a feel for what the surface is like. And then fill in your mind, your mind will fill in the blanks so that you're actually looking at that. That's the surface we're looking at here. Double cone. So just a quick example then of a transformed version. This is our reference double cone. A transformed version would be. So we could say like y minus 1 squared equals x squared over 4 plus z plus 2 squared. Okay, so this would have all 3 transformations. So where would our vertex be, first of all? It'd be at 0, 1, negative 2. So 0, 1, negative 2. So vertex this way. Which way does this open? It's going to open in the y direction. Yep. And then in terms of now, it's going to be elliptical. And we're going to have a ratio of x radii to z radii of 2 to 1. So it's going to be kind of like this. Imagining some traces, some vertical traces for constant y values. So something like that. So wider in x, 2 times the width in x than it is high in z. And then centered now at this point, 0, 1, negative 2. Down here below the y-axis.
And it's a 4 on the bottom because 2 squared equals 4, right?
It's a 4 on the bottom, so then the ratio of the radii is 2 to 1. Right, so this is 2 squared. So this is kind of like the radius in the x direction is like 2, but it's really a ratio because those radii are always getting bigger. Did that answer it?
Yeah, I was just trying to remember if it was squared or not.
So whatever number is your denominator is the radius squared. So 4 is the radius in the x direction squared, meaning that that radius is 2. But again, it's a ratio because it's always changing. So it's a ratio of radii, 2 to 1. Okay, other questions? So we just added to our repertoire here, double cones.
So we need to be able to recognize these by their equations and their shapes for the test.
Yeah, so given the graph, recognize the equation, given the graph, can like come up with the equation. Given the equation, come up with the graph. Yes, exactly. And then this will be both on exam 1 and exam 2 because and then the last part of the course is using these surfaces, like we need to have them down pat because we're going to be doing these more complicated, harder problems that involve surfaces, and we don't want to be spinning our wheels trying to remember what the surfaces are. So learn them for the exam one, and don't be in the mindset that you can move on. So just learn them to learn them for good. Okay, other questions? All right, so then we'll start exam 2 material here today. And then that topic is called vector functions. Vector functions. So where are we? PowerPoint. There we go. So vector functions. So vector functions, we know the idea of a function is that there's an input quantity or thing, and then there's a output quantity or thing. So it's like independent and dependent, right? So independent. So the idea of function is that you have an independent that's very wrongly spelled, but you got it, independent and a dependent. So, you know, your basic functions that you've lived with your whole math career have been, the independent variable was a scalar, right? X was a real number, and for every real number, you got exactly one real number y. So both your independent variable and your dependent variable was a scalar or a real number. Okay, so that's called a real valued function. Real valued means that what comes out is a real value. So a vector function, we still have, as with all functions, we have an independent thing and a dependent thing. The independent thing is still a scalar. We usually call it t. So the independent is a real value. Okay, and then now, but what comes out? So given a real value, instead of getting another real value, we get a vector. Okay, so what goes in for every real value, the function assigns a vector. And the way it assigns it a vector is by 3 separate real valued functions, right? So there's a real valued function for x, a real valued function for y, and a real valued function for z. And that forms the vector that you get for whatever value of t there is. Okay, so vector functions are the independent thing is a real value, usually t, and then for every real value, the function gives a vector. And the way the function gives a vector is by 3 separate real valued functions of t for the x, the y, and the z. So a domain now, so the domain would be all values of t that make all 3 component functions legitimate or defined. So any t value that makes one or more of these undefined is not in the domain for the vector function. So we want all values of t that make all of the components x, y, and z defined. As soon as you get one of the components non-defined, well, that's a non-defined vector, so it's not in the domain. The t value is not in the domain of the vector function. So any questions on the idea of a vector function? Given a real value, the function gives a vector in return. Okay, so how do we graph these?
You plug t into all the functions, right?
Okay, right. So yep, you plug t to get you plug t into all the functions to get the vector corresponding to that real value t.
Is this going to be on the test?
Nope, this is starting exam 2 material now.
Okay, thank you.
Yep. The surfaces is that double cone. Surfaces is the last thing for exam 1. Okay, so here is a vector function, and it's this one right here. Now it's written vertically, but normally when you write it or you see it in a textbook, it'll be horizontal. So you want to write it this way. So this vector function is, given a value of t, the x component is cosine of t. The y component is this polynomial here. And the z component is 1/2 sine of 5t. So a pretty complicated vector function here, okay? But for our purposes right now, that's fine. So what, and like we said, for every value of t, so say here's t equals 1.15. Does that show up down there at the bottom? Let's see. Let's do this. So here's t is 1.15. We get a vector. So the vector that we get is shown here in R3. So it has a positive x component, looks like negative y component, and it looks like a negative z component as well. And you get those components by plugging t into these values, into these expressions. Okay, so and when t is, back here, when t is negative 0.62, you get a different vector. You get this vector, which has a z component pretty close to 0, it looks like. So every t value that I could pick generates a vector. That's a vector function. Every t value generates a vector. So now the graph representation is we're going to take all those vectors and put them in standard position, as I'm showing here. So here's different t values and different resulting vectors in standard position. So if you let t vary continuously, it's those vectors in standard position sweep in space, right? And so if we focus on the tips of those vectors, the coordinates are the same as the components because we're in standard position, right? So any location, so say right here, so the coordinates of that point are the same as the components of the vector, or the output quantity of this function. So if we let the tips, the coordinates of the tips, which represent the components of the vectors, sweep out a curve. This curve then, any given point on the curve, the coordinates represent the components of the vector for some value of t. And so then so let's see if I can pause it on that one here. Negative 0.56. So this is when t equals negative 0.56. Oh, that's so unfortunate. Help me. Come on. All right, we're back. Okay, don't do that again. Draw. All right, so this is t equals negative 0.56. And that's giving some vector. And the components of that vector, this vector, black vector right here, are the same as the coordinates of that point, because I put the vector in standard position. So the coordinates of all these points represent the vectors that you get from the vector function for each value of t. And when you sweep it out for continuous, when you sweep out all the vectors and sweep out all the points for the different values of t, you get a curve in space. So a representation of a vector function is a curve in space. And that curve comes from the vectors we get in the function. Okay, so does the idea that a vector function, it takes a real value, it gives back a vector. When you let those real values vary and put those vectors on in standard position, then those vectors sweep out a curve whose coordinates are the same as the components of those vectors. So that curve in space is a representation of the vector function. Okay, any questions so far? Okay, so let's look at a slightly easier vector function and talk about that. So here's one. This is a more straightforward function.
Quick question.
Yeah, please. Always.
So, vector functions are always going to be set up in the format of a vector, but instead of an actual scalar unit, among each position, it's going to be a function in each position. Does that make sense?
Not 100. There were definitely some bits in there you said that were correct, but kind of putting together, I wasn't sure.
So how you set up a normal vector is you have your little your arrow kind of ish thing, yeah. And so when you have a normal vector, instead of saying, having t and then sine 2t and then 0.5 e to the t, you usually have a number that represents that vector, which will have numbers for these vectors. But for the vector function, you have a function within each of those spots instead of a numerical value, right?
Yeah, but we're gonna, for every value of t, we're gonna get a vector with numerical values.
But for the function of it.
Well, but the function is a set of vectors. So the function results in a set of vectors. Every one of those vectors has number values for the components. So this is just a representation of like all the vectors that you would get.
The one thing I'm saying is that it doesn't just put like numerical values into it.
Well, you could have a constant, this is a totally valid vector function. It means for any value of t, you always get the same vector. So that's a vector function too. So I don't know if that like upset your apple cart a little bit there, but does that make sense? That's a valid vector function. It's just a constant function. You get the same vector for every t. Is it okay?
Yep.
Okay. Yeah. So they don't. You could have constants in here. You could have constants in here that just then that component wouldn't change as t changed. Okay, I hope that. Please ask me later if I'm still haven't answered your question. All right. So for this one, here's a little more basic function. So we want to. Our goal is, given a vector function, be able to sketch it and be able to sketch the space curve that it is. So one way to do that is to kind of isolate this because we're in 3 dimensions. There are different faces of this. There are different views, right? There are different views, and so there are 3 views in particular that we're interested in, and that's like the projections into the coordinate planes. So for instance, let's just focus on x and y together. So here x equals t and y equals sine of 2t. And if you remember back from, so what is this really? This vector function is really almost like something you did in Calc 2. Does anybody remember? This is basically the same thing as what? Yeah, this is basically the same thing as parametric equations, but now we're going to just take all those expressions and throw them into a single vector. That's the only difference. So, and then we're going to call it a vector function. Okay, so this is like the twin brother of parametric equations, these vector functions. So if I want to isolate and just take a look at just x and y, okay, just x and y, and back, if you remember in Calc 2 when you did these, you saw that you could combine these and eliminate t and get an equation of x and y. So what would the equation of x and y be for this?
Y equals sine of 2x.
Yeah, so if t is x, then we can substitute x there because t is x, right? T is equal to x. So y equals sine of 2x. So y equals sine of 2x is a perspective. It's a perspective on the space curve that we get from this vector function. What perspective is it? It's the perspective that doesn't care about t, doesn't care about distinguishing between t values. So how should I look at this graph? How should I look at this graph to do that? How should I look at this graph to only see the relationship of x and y and not have z be involved?
Correct.
You cut off there. So
So you should look at it directly from the top down.
right. So if I take this and I look at it top down the z-axis, I won't be able to see changes in z anymore. And what will happen?
It'll be a sine graph,
Which sine graph?
sine of 2x.
Yeah, it'll be this graph, right? So now you can't see changes in z. All you can see is how x and y are related, and we know how x and y are related by y equals sine 2x. There it is. There's the curve y equals sine 2x. All right, we do the same thing with, so this is the projection of r into the xy plane. When you project the curve, the three-dimensional space curve, into the xy plane, you get this curve, and we show that algebraically as well. Okay, so what about into the xz plane? What curve will I get in the xz plane?
1/2 e to the x
Equals what?
equals z.
Equals z, right? Because x equals t. If x equals t, then I can put x there, and z equals 1/2 e to the x. So how will I see this perspective of the space curve that just shows the x and z relationship?
Turn the graph around so that you are just perpendicular to the xz plane.
Yeah, so I'm gonna look right down the y-axis, so I can't distinguish y values anymore. I can't see variations in y, but only here's x to the right and z is up. And so if I get that just right, what do I see?
The graph of 1/2 e to the x.
Yeah, there it is. There's 1/2 e to the x. It's the same curve I showed you at first. It's the same space curve, but it's only the xz plane projection. It's a projection into the xz plane, which is only going to show this relationship between x and z. Now we can also go ahead.
Yeah. So the way that you would actually check to make sure that you did it correctly is by actually well, we couldn't necessarily do that on just paper, but if you have a system, you could look at it based off the way that it actually looks. Like, for example, we saw sine of 2x. It should look like a sine graph right there on the what was it, on that plane versus the other, versus the one.
Yeah, that's what I showed you earlier, right? There's the xy plane. Yeah, there's the xy plane.
Right.
There's y equals sine 2x. Here's the xz plane. There's z equals 1/2 e to the x. So the last one is not such a simple one because it brings together a sine and exponential, but we can still do it. And then the graph can tell us what this unfamiliar thing would look like. So we got y equals sine 2t and z equals 1/2 e to the t. And so in order to get this equation of y and z, let's solve this one for t. So what would t equal? T is going to equal natural log of 2z. Multiply by 2, inverse function of exponential is natural log. So now I can take that and put it here, and so what do I get? which is unfamiliar, right? This is, did I get that right? Is there a 1/5 or something?
Shouldn't it be like a 2 multiplied
Yeah,
by
yes,
that?
thank you. I knew something didn't feel right there. Thank you. Do I have it right now?
Yes. That's good.
Okay, so what does that look like? Who knows, right? So it's like this is not a basic, this kind of crazy, complicated thing, that's sine of 2 natural log of 2z. But we have the means to now know what that curve looks like. So and how would I do that? Yeah, I'm going to get rid of the x component now. So I'm going to look down the x-axis. I'm going to put y to the right and z up. And see what we get. So it's going to be this thing that oscillates like a sine curve, but the period's going to keep decreasing and decreasing. So it's going to, down here by the xy plane, it's going to oscillate really fast. And then as z increases, your period's going to get bigger and bigger and bigger, so that it's sweeping longer and longer without oscillating. The amount of oscillation is going to decrease greatly per increase in z. But as you get, like I said, as you get closer to 0, then it's just going to oscillate faster and faster, or that period's going to shrink. Put it all together, and you get, consider all 3 components, and you get this space curve. Okay, so this is one thing that we're going to use to so an important thing is to identify these vector functions as space curves, maybe be able to sketch them. So this is going to be one really important technique, is isolating 2 variables, coming up with that equation, and that's going to be how the curve projects into that given plane. So let's look at some basic examples here. And what time are we done here? 12. So we got 6 minutes. Good. Okay. So here's just a little, you can write this down later. Don't take the time to write this down later. But sketching R3 curves, we want to recognize basic parametric functions from Calc 2. Formed by pairs of equations of x, y, and z. Okay, so we're gonna pair together x, y, and z, and recognize parametric functions that we did in Calc 2. Sometimes we're gonna use algebra to eliminate t from those pairs of equations. We need basic knowledge of just basic R2 curves, pre-calc, algebra, and then just sketching the projections first to try to imagine what the curve will look like later. In space, right? So it's just in terms of identifying and sketching these curves, as we're bringing together lots of tools from your past experience in Calc 2 and in pre-calculus, but then also like what I just showed you, this idea of projections. All right, so here's this first one, and so for this one, our interest here is in x and z, right? We see that x is sine t, and z is cosine t. Okay, so do we want to solve for t and plug into the other one? No, because that'll be like the inverse trig function of a trig function, and that's not convenient. But this is actually a very natural parameterization for something that we should know. Do we recognize if one variable is sine and another variable is cosine? We should know what we get. My experience is that often we don't, but so maybe today's the day that everyone's going to know. What do you get when one function, one variable is sine and another is cosine?
Parametric function for a circle.
Circle. Okay, so if that wasn't on the tip of your tongue, today's the day when, by very definition, sine and cosine are the coordinates on a circle, right? So your unit circle, you sweep out an angle, in this case t. The x coordinate of that point is cosine t, it's the x coordinate. The y-coordinate of that point is sine t. So whenever you have two variables assigned to sine and cosine, you take them together, those equations taken together give you a circle. In this case, a unit circle, radius of 1. You might get an ellipse too if we stretched or shrunk one of these, or both, and you can get an ellipse too. All right, and where does that circle live? Looking at this function, where will that circle live?
On the xz plane.
Right, and specifically the xz plane, why? Because y equals 0. So for all these points of this function, y is 0, and that is the xz plane. And then we're going to have the unit circle in the xz plane. So if I can turn that on. Give it a spin. Okay, so that's what this vector function is. Sine t, 0, cosine t. Unit circle in the xz plane. And we can imagine that being swept out by vectors in standard position as t increases, right? So imagine a vector just going, just with its tail at the origin, just looping around, and its tip casting out all these points on the unit circle. Okay, what about the next one? Let's take a look at this next one. So here I have x equals 1 plus 3t, y equals 0 minus t, and z equals negative 2 plus t. And you look at that and you say, aha, I know what that is. Because I'm an expert at this. I just did my homework.
It's a line.
This is the parametric equations of a line that we learned a couple lectures ago. And you like I said, you became experts in the homework. So if you have 1 plus 3t, 0 minus t, and negative 2 plus t, we just saw that in a different form. We just kind of had decomposed that, right? What's the decomposition of that? It's vector 1, 0, negative 2, plus t times
3, negative 1, and 1.
Good. So we already did vector functions. We already did a specific kind of vector function, which was lines, right? So a line is just a straight curve. We said vector functions give a curve in space. A line is just a type of curve that's straight. So we were doing a type of vector function when we learned lines. We just didn't know it. Okay. So it's easy to sketch because we know how to sketch. So we've got our point on the line. So 1, 0, negative 2. And then we can put the tail of our direction vector here. So 3, 1, 2, 3, negative 1, positive 1. Draw the vector. So I got my point. I can put my direction vector on there, and then got my line. So when we learned lines, we were learning a specific kind of vector function, which graphs as a curve in space, but in that case, a straight curve in space.